Somewhere above us right now, a small spacecraft is moving faster than anything human hands have ever built. It is falling past the sun, again and again, on a long looping path, and each time it swings by, it picks up a little more speed. Tonight, let's follow that spacecraft for a while, and let it lead us into a much bigger question. How far could a person actually travel in one lifetime? Out into the vastness of space. It's a gentle question, but it opens into something enormous. So let's take our time with it. The spacecraft is called the Parker Solar Probe. It launched in the year 2018, and during its closest passes by the sun, it reaches speeds of more than 430,000 miles per hour. That's a hard number to hold in your mind. So here's a way to feel it instead of just hearing it. At that speed, the probe could cross the entire continental United States in well under 30 seconds. If you were standing in New York and you blinked twice, slowly, the spacecraft would already be somewhere over the Pacific, well past Los Angeles, drifting toward Hawaii. It's the fastest thing we've ever made, and it took nearly all of what we have as a species to make it. Decades of careful engineering went into it. Billions of dollars. Thousands of scientists and engineers working across generations, refining trajectories down to fractions of a degree. The probe doesn't get its speed from a single powerful engine. Instead, it uses a series of gentle gravitational nudges from Venus, flying close to the planet again and again, stealing a little bit of orbital momentum each time, building speed gradually. The way a child on a swing gets a little higher with each push to understand just how remarkable that speed really is. It helps to look back at the long, slow history of how fast a human being has ever moved. For most of the time our species has existed, roughly 200,000 years, the fastest a person could travel was about as fast as a galloping horse. Somewhere around 25 miles per hour. That was the ceiling. For nearly the entire span of human history, that was as fast as a human body had ever gone. Then, within just the last 120 years or so, everything changed very quickly. By 1900, early automobiles were reaching past 60 miles per hour. In 1903, the Wright brothers lifted off the ground at about 34 miles per hour and stayed up. Within 6 decades of that first flight, test pilots had broken the sound barrier, reaching speeds of 761 miles per hour. And by 1969, astronauts returning from the moon were moving at nearly 25,000 miles per hour, which remains, even now, the fastest any human being has personally traveled. The Parker Solar Probe moves about 17,000 times faster than those returning Apollo astronauts. No person could ride aboard it. Not really because of the speed itself, but because its path carries it so close to the sun that it experiences temperatures above 2,500 degrees Fahrenheit. The probe survives that with a heat shield. A human body would not. So here we have, in one machine, the absolute outer edge of everything humanity has learned about moving quickly through space. And now here's the quietly humbling part. Even at 430,000 miles per hour, the Parker Solar Probe would need about 6,600 years to reach Proxima Centauri, the nearest star beyond our own sun, just over 4 light years away. Think about what 6,600 years actually means. If a journey like that had begun around the time the ancient Sumerians first started writing things down, it would only now, today, be getting close to arriving. A human life lasts roughly 80 years. Traveling for that entire lifetime at our fastest achieved speed, a person would cover barely more than 1% of the distance to the nearest star before their life came to its natural end. Let's sit with that for a moment, because the scale of it is worth absorbing slowly, traveling continuously. For 80 years, at the Parker Solar Probe's peak speed, You would cover about 3 trillion miles. Written fully out, that's a number with 12 zeros after it. It sounds enormous, and in everyday terms, it is. But measured against the true distances between stars, 3 trillion miles comes out to only about 5/100ths of a light year. The nearest star system sits more than 80 times farther away than that. An entire human lifetime spent traveling at our absolute fastest wouldn't get you 1/10 of the way out of our own stellar backyard. There's another boundary worth mentioning here, called the Oort cloud. It's a vast, thin shell of ancient icy debris, the leftover material from the formation of our solar system, surrounding the Sun at a distance of up to about 100,000 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. The Oort cloud marks the place where the Sun's gravity finally loosens its grip. The true edge of our solar system, where interstellar space genuinely begins, at our fastest current speeds. Simply reaching the inner edge of the Oort cloud would take roughly 600 years. An entire human lifetime, even at the most extreme velocity we've ever achieved, would not be enough to leave the gravitational reach of our own Sun. We would live and die long before crossing out of our solar system's own backyard. Measured against the true scale of even our closest cosmic neighborhood, a full human life of travel would be something like walking from one side of a single city block to the other. It helps to look at an actual spacecraft that has spent decades doing exactly this kind of traveling. Voyager 1 has been moving outward for more than 47 years now, and it holds the record for the most distant human-made object from Earth. In that time, it has covered about 15 billion miles, half a century to cover that distance, and it keeps adding to the total every single second. In 2012, Voyager 1 crossed something called the boundary where the Sun's outward stream of charged particles, the solar wind, finally gives way to the thin gas and dust that drifts between stars. At the time, headlines said Voyager had left the solar system. That's true in one narrow sense, and quite misleading in a broader one. The probe escaped the Sun's magnetic influence, yes, but it remains completely within the Sun's gravitational pull, and it won't pass beyond the Oort cloud for another 30,000 years or so. 15 billion miles sounds like a remarkable distance, until you compare it to what's actually required. It comes out to less than 0.03% of the distance to the nearest star. Here's a way to picture that scale. Imagine the entire journey to Proxima Centauri laid out as a cross-country drive from New York to Los Angeles. Roughly 2,800 miles of highway. On that scale, Voyager 1, after 47 years of continuous travel, would have moved about 100 feet. You'd still be standing in your own driveway, barely past the mailbox. After half a century on the road, your neighbors would have watched you grow from a young person into someone nearing retirement, all while your car sat there, just barely out of the garage. Here's one more way to feel the scale of it, using light itself. Light moves at about 186,000 miles per second. In roughly the time it takes to read this sentence, light has already circled the entire Earth 7 times over. Voyager 1, after almost 5 decades of travel, has covered a distance that light crosses in about 20 hours. The probe's entire 47-year journey adds up to less than 1 day of light's own travel. The trip to Proxima Centauri represents more than 100,000 times the distance Voyager has managed in nearly half a century. Voyager 1 moves at about 38,000 miles per hour relative to the Sun, which is extraordinary by the standards of anything built on Earth, but reveals just how wide the gap is between what we've achieved and what interstellar distance actually demands. At that speed, reaching Proxima Centauri would take over 70,000 years. When Voyager 1 eventually arrives at the distance of our nearest stellar neighbor, assuming it even survives that long in the thin sleet of interstellar particles. The civilization that built it will have been gone for far longer than our species has currently existed. Modern humans, Homo sapiens, have been around for roughly 300,000 years. Voyager would need to travel for nearly a quarter of that entire span, just to cover the distance to the closest star, and it won't make it that far in any working sense. Voyager 1 runs on a plutonium power source, generating electricity through the slow decay of radioactive material. That power source loses a small amount of wattage every year as the fuel depletes. By the mid-2020s, it will no longer have enough power to run its scientific instruments. By around 2036, it will fall silent completely and continue drifting, a quiet, dead piece of human history, tumbling through the dark for tens of thousands of years, never arriving anywhere, never seen again by any human eye. So why is this so hard? Why can't we simply build something faster? The honest answer lies in basic chemistry. Every rocket we have ever launched works on the same principle that lifted the earliest fireworks into the sky over 1,000 years ago. You throw mass out the back, and the spacecraft is pushed forward in response. It's Newton's third law, doing exactly what it always does. Simple, elegant, and, for the purposes of reaching another star, deeply limited. There's a mathematical relationship called the rocket equation, worked out by the Russian scientist Konstantin Tsiolkovsky back in 1903, that describes the hard ceiling chemical rockets run into. Tsiolkovsky was a deaf schoolteacher living in a small provincial town, largely self-taught in mathematics and physics, who spent years thinking carefully about what would actually be required to leave the Earth's atmosphere. He never built a rocket himself. He worked it all out on paper, through patient calculation, arriving at an equation that still governs every rocket launch humanity has ever attempted more than a century later. Decades after Tsiolkovsky, other early pioneers, including the American physicist Robert Goddard and a small German rocketry society, began testing the practical side of his theoretical work, building and flying the first liquid-fueled rockets, slowly turning Tsiolkovsky's equations into working hardware. It depends on two things: how fast the rocket can throw its exhaust out the back, called the exhaust velocity, and the ratio between the rocket's fuel-laden mass at launch and its much lighter mass once that fuel is spent. For chemical fuels, the maximum practical exhaust velocity tops out at around 4.5 kilometers per second. That's not a limitation we simply haven't engineered our way around yet. It's a hard ceiling set by the chemistry of combustion itself. When hydrogen burns with oxygen, one of the most energetic reactions we can practically use in a rocket, the resulting steam molecules can only move so fast as they leave the nozzle. No amount of clever design changes that dot the consequences of this ceiling become almost absurd once you start running the numbers for interstellar travel. To accelerate a small probe, something around 1,000 kilograms, to just 1% of the speed of light, using only chemical rockets, the fuel required would exceed the total mass of the entire observable universe, not the mass of the Earth, not the mass of the Sun, not even the combined mass of every star in our galaxy. The mass of every galaxy, every star, every planet, every atom that exists anywhere in the observable cosmos, still wouldn't be enough chemical fuel to get a small car up to 1% of light speed. That's not an exaggeration for effect. It's simply what the mathematics requires. The rocket equation behaves exponentially, and that exponential curve climbs so steeply that it quickly demands more matter than physically exists. Gravitational assists offer some relief. The technique the Parker Solar Probe and the Voyager probes both rely on. By timing a close flyby of a massive planet carefully, A spacecraft can borrow a small amount of that planet's own orbital momentum and convert it into extra speed, at no fuel cost at all. Jupiter, for instance, moves very slightly slower around the Sun after each spacecraft that's used it for a boost, though the change is far too tiny to ever measure. The spacecraft, meanwhile, gains a substantial kick in speed, but gravity assists have their own limits too. There are only so many large planets in our solar system positioned usefully for this kind of maneuver, and each flyby costs years of travel time to set up. A spacecraft built specifically to chain together gravity assists over a decade or more of patient planning might eventually reach something like 150,000 miles per hour. That's about 4 times Voyager's current speed. Still nowhere near enough. Still requiring tens of thousands of years to reach even the nearest star, the fastest spacecraft to leave our solar system. Primarily using this technique is New Horizons, which flew past Pluto in 2015 after a major speed boost from Jupiter back in 2007, reaching about 36,000 miles per hour relative to the Sun. It sent back the first close images of Pluto, revealing a world far stranger and more beautiful than anyone expected, with nitrogen, glaciers, and mountains made of water ice. Even at that impressive speed, the journey to our nearest stellar neighbor would still take more than 80,000 years. There are other propulsion ideas, each a small improvement. None of them enough. Ion engines work by ionizing a propellant, usually xenon gas, and accelerating the charged particles using electric fields. The exhaust leaves the engine 10 to 20 times faster than anything a chemical rocket can manage, which makes ion engines remarkably efficient for maneuvering within the solar system. The Dawn spacecraft used this technology to become the first mission ever to orbit 2 separate bodies beyond Earth, drifting gradually from one orbit to another over months of gentle, continuous thrust, but the thrust itself is tiny. Dawn's ion engine produced a force of about 90 kilonewtons, which is roughly the weight of a single sheet of paper resting on your palm. That tiny push, applied patiently over years, can build real speed eventually. But even with unlimited fuel and a century of continuous operation, an ion engine still couldn't get anywhere near the velocities interstellar travel requires within a human lifetime. Nuclear thermal rockets do a bit better. They work by passing hydrogen propellant through a nuclear reactor, heating it to extreme temperatures before it's expelled through a nozzle, roughly doubling the exhaust velocity compared to chemical combustion. NASA tested this technology extensively through what was called the NERVA program, through the 1960s and into the early 1970s, running dozens of successful reactor tests. The technology worked. It was ready. Political and budgetary decisions ended the program in 1973, and we simply chose not to continue. We've known how to build a working nuclear rocket for more than 50 years. A nuclear thermal rocket could theoretically reach about 100,000 miles per hour with a reasonable amount of fuel, roughly triple what chemical propulsion alone can manage. At that speed, the journey to Proxima Centauri would drop to about 28,000 years. Still far longer than any human lifetime. Still longer than recorded civilization has existed. But meaningfully better. Solar sails take a different, almost elegant approach. They carry no fuel at all, relying instead on the gentle pressure of sunlight itself. When photons strike a reflective surface, they transfer a tiny amount of momentum, nudging that surface gently in the direction the light was traveling. A large, extremely lightweight sail could gather this pressure over time and slowly build speed. Japan's Icarus spacecraft demonstrated this in 2010, unfurling a 14-meter reflective membrane and measurably accelerating from sunlight alone. It proved the idea works in practice, not just on paper. Close to the sun, where sunlight is most intense, a solar sail could accelerate at roughly 1% of Earth's surface gravity. That sounds promising, until you remember that the whole point of a journey is to go somewhere else. And as the sail moves away from the sun, the available light drops off sharply, following an inverse square relationship. Double the distance, and you're left with only a quarter of the push. The acceleration that felt meaningful near the sun fades to almost nothing by the outer solar system, and vanishes entirely once you're out in interstellar space. A sail launched from a close pass by the sun might reach somewhere around 500,000 miles per hour before the sunlight becomes too weak to help anymore. At that speed, about 100 times Voyager's velocity, faster than anything ever built, the journey to the nearest star would still take more than 5,000 years. A full human lifetime traveling at that speed would cover only about 6/10 of a light year, something like 1/17 of the way to Proxima Centauri. You would die in the empty space between the stars, having made real progress, but nowhere near arriving. This is the honest, sobering picture of what's actually achievable with the propulsion technologies we've built, tested, or could plausibly construct within the coming century. Chemical rockets are fundamentally incapable of the task. Ion engines are too gentle. Nuclear thermal rockets help, but not nearly enough. Solar sails can't push a large mass fast enough to matter. By every measure we currently have, we seem permanently confined to a small bubble just a few light hours wide, centered on our own sun. It's easy to see why, for much of the 20th century, many physicists quietly concluded that interstellar travel for living beings was simply impossible. The distances seemed too vast. The energy requirements seemed absurd. The years spent traveling through deep space would expose a crew to a steady accumulation of cosmic radiation that no shielding could fully block. It felt, too many serious thinkers, as though the universe had built a kind of natural quarantine around every star system, keeping any intelligent life quietly sealed inside its own solar neighborhood. We might send and receive radio messages across the gulf, over years or centuries, but never visit, never set foot anywhere else, never shake hands with whatever else might be out there. That was the prevailing, careful, well-reasoned conclusion, held by people who understood the engineering involved as well as anyone alive. It wasn't pessimism for its own sake. It was simply where the mathematics seemed to lead. Every time anyone ran the numbers honestly, and then, in the spring of 1905, a 26-year-old patent clerk in Bern, Switzerland, sat down and asked a very simple question that would quietly undo all of it. His name was Albert Einstein, and the question he asked himself was almost childlike in its simplicity. What would it actually look like, he wondered, if you could ride alongside a beam of light? What would you see? How would time behave around you? The answer he worked out overturned 3 centuries of assumptions about how motion, time, and distance actually function. What Einstein found was that the speed of light in a vacuum is the same for every observer, no matter how fast that observer happens to be moving. Whether you're standing still on the ground or racing through space at half the speed of light, you will always measure light traveling at exactly the same speed, about 186,282 miles per second. This isn't some quirk of measurement. It's woven into the basic structure of reality itself. From that one simple, almost stubborn fact, something else has to give. And it turns out that something is time. A clock aboard a fast-moving spacecraft runs slower than an identical clock that stays behind. This effect is called time dilation, and when it was first proposed, it sounded almost absurd. How could time, the most fundamental, universal thing we know, run at different speeds depending on how fast someone happens to be traveling? And yet the mathematics held up perfectly, and within a few decades, careful experiments confirmed exactly what Einstein had worked out from pure reasoning alone. Time dilation is real, it's measurable, and it changes everything about what's possible for a human traveler. There's a precise number that describes exactly how much time slows down at any given speed. Physicists call it the Lorentz factor, usually written as the Greek letter gamma. You find it by taking 1 and dividing it by the square root of 1 minus your velocity squared divided by the speed of light squared. It looks complicated written out like that, but the numbers it produces are what make interstellar travel within a human lifetime theoretically possible at ordinary, everyday speeds. Gamma is so close to 1 that the difference is meaningless. A car on the highway experiences a kind of time dilation so small that only the most sensitive atomic clocks could ever detect it. A person flying across the country ages a few billionths of a second less than someone who stayed on the ground. Real, but utterly without practical consequence. The effect becomes meaningful only once you start approaching a substantial fraction of the speed of light. At 50% of light speed, gamma reaches about 1.15. Time aboard a ship moving that fast passes about 15% more slowly than time back on Earth. 1 year aboard the ship corresponds to a little over 14 months back home. Noticeable, interesting, but not yet transformative. Push to 90% of the speed of light, and gamma jumps to roughly 2.3 for every year that passes for the traveler. About 2 years and 4 months pass back on Earth. A 50-year journey at this speed would leave the traveler having aged 50 years, while people back home aged closer to 100. The crew would return to find their grandchildren elderly, and their great-grandchildren already running the world they left behind. Push further to 99% of light speed, and gamma reaches about 7.1. 7 years pass on Earth for every single year experienced by the traveler. A decade of life aboard ship corresponds to 70 years back home. A 50-year journey, from the traveler's own point of view, would span 355 years of Earth's history. You would leave one civilization behind and return to find a completely different one in its place. At 99.9% of light speed, GAMMA passes 22 years of Earth time compress into a single year aboard the ship. 50 years of travel, for the crew, would correspond to about 1100 years passing back home. More time than has passed since the fall of the Roman Empire. The pattern continues as you inch ever closer to light speed. At 99.99%, gamma passes 70. At 99.999%, it surpasses 223. Each additional 9 you add to the percentage pushes the time dilation factor up by roughly another threefold. The closer you get to light speed, the more dramatically time bends in the traveler's favor. Let's make this concrete with some actual destinations. Vega, one of the brightest stars in our night sky, sits about 25 light-years from Earth at ordinary spacecraft speeds. Reaching it would take hundreds of thousands of years, far beyond any human lifetime. But traveling at 99% of light speed, with gamma at about 7.1, the picture changes completely. From Earth's perspective, the journey still takes about 25 years, because nothing can move faster than light itself. But for the traveler aboard the ship, that same journey compresses down to roughly 3.5 years. You could travel to Vega, look around at whatever worlds might orbit that brilliant blue-white star, and return to Earth having aged only about 7 years, while 25 years passed back home push the speed up to 99.9% of light speed, with gamma near 22, and that same round trip to Vega compresses to a little over a year of subjective time. You could go, explore, and come home, all before your second birthday aboard the ship. while Earth aged about 50 years in your absence. The Pleiades star cluster, that lovely group of hot blue stars visible to the naked eye on winter nights, sits about 440 light-years away. At conventional speeds, reaching it would take millions of years. At 99.9% of light speed, with gamma above 70, the subjective journey time drops to around 6 years each way. You could travel to one of the most storied star clusters in human mythology, explore several of its stellar systems, and return having aged perhaps 15 years, while nearly 900 years passed on Earth. The center of our own galaxy lies about 26,000 light-years from here, home to a black hole with roughly 4 million times the mass of our Sun, surrounded by dense star clusters and energetic phenomena unlike anything found elsewhere in the Milky Way. At 99.999% of light speed, with gamma above 223, the subjective journey there falls to around 116 years. Still a long voyage by any measure, but no longer an impossible one. And then there's Andromeda, our nearest large neighboring galaxy, about 2.5 million light-years away, a spiral structure even larger than our own Milky Way, home to perhaps 1 trillion stars and, conceivably, countless worlds. At velocities where gamma reaches around 1 million, speeds so close to light that the remaining gap becomes almost a philosophical question rather than a practical one. The subjective travel time to Andromeda drops to about 2.5 years. A traveler could cross the gulf between galaxies, explore an entirely separate island of stars, and experience the whole journey as lasting less time than an average graduate program. Earth, meanwhile, would age 2.5 million years during that same trip. Whatever civilization exists back home upon return would almost certainly be unrecognizable, or simply gone. These numbers point to something genuinely surprising. The universe doesn't seem to have been built to prevent cosmic exploration. Time dilation offers a real, physically valid pathway for human consciousness to cross distances that light itself needs millions of years to traverse. What stands in the way isn't physics, it's engineering. The equations permit travel across interstellar and even intergalactic distances within a single human lifetime. We simply don't yet have the means to reach the speeds required. So why does reaching those speeds demand so much energy? The answer traces back to another of Einstein's well-known results, the equation that connects mass and energy. Mass and energy, it turns out, are two expressions of the same underlying thing, interchangeable under the right conditions. This has consequences for anything trying to move at a meaningful fraction of light speed. At low, everyday velocities, the energy needed to speed up follows the simple rules Newton worked out centuries ago. Double your speed, and you need 4 times the energy. Straightforward, and with no hard limit, as long as you have enough fuel. But as an object's speed climbs toward a significant fraction of light speed, something stranger starts happening. The energy required to keep accelerating grows much faster than Newton's equations would predict. It begins to behave as though the object has gained extra mass, an effect called relativistic mass increase, and it grows more dramatic the faster you go. At 50% of light speed, an object behaves as though it weighs about 15% more than it did at rest. At 90% of light speed, that effective mass has more than doubled. At 99%, it's increased by a factor of about 7. At 99.9%, the factor passes 22. Every additional bit of speed costs not just a little more energy, but dramatically more. This is the same gamma factor that gives travelers their time dilation benefit. But here it works against them, demanding ever steeper energy costs as they push closer to light speed. As velocity approaches the speed of light, the effective mass approaches infinity. And accelerating an infinite mass would require infinite energy, since infinite energy simply doesn't exist. The final approach to light speed becomes something you can get closer and closer to, forever, but never quite reach. The actual energy numbers involved are staggering, even well below this theoretical wall. Accelerating a small probe, something around 1,000 kilograms, to 90% of light speed requires more than 10 to the 19th power joules of kinetic energy. Written fully out, that's a number with 20 digits. It's roughly equal to the total energy our sun puts out in about 2 seconds, or the entire energy consumption of human civilization across roughly 1,000,000 years, all concentrated into accelerating a single small spacecraft for something closer to a real vessel, large enough to keep a human crew alive during the journey, with a mass of 100,000 kilograms or more. The energy requirement scales up proportionally. Accelerating a vessel that size to 90% of light speed would demand energy equivalent to the sun's total output across several minutes. And remember, travelers generally want to slow down once they arrive. Decelerating from 90% of light speed costs exactly as much energy as the original acceleration did. A full round trip, accelerating, then doing it all again for the return leg, multiplies the total energy requirement by 4. No propulsion system humanity has ever built, tested, or even seriously proposed can deliver energy anywhere near this scale. Chemical rockets fall short by a factor of billions. Nuclear fission improves things, but remains nowhere close to sufficient. Even nuclear fusion, the very process that powers the sun itself, struggles to provide the energy density that practical relativistic travel would actually require. There's also a gentler, more human constraint worth mentioning, which has to do with comfort rather than energy. People can tolerate continuous acceleration at one Earth gravity more or less indefinitely. It simply feels like normal weight, letting a crew walk, eat, sleep, and live something close to an ordinary life throughout the journey. Higher accelerations become uncomfortable and eventually dangerous. Sustained acceleration at 2 Earth gravities causes real fatigue over time. 5 gravities can cause people to black out. 10 can be fatal at a steady, comfortable 1 gravity of continuous acceleration. A spacecraft would reach 90% of light speed in about 11 months. The natural approach for a long journey would be to accelerate at 1 gravity for the first half of the trip, then flip the ship around and decelerate at the same gentle rate for the second half, arriving at the destination at rest rather than screaming past it. 1 year of this kind of steady acceleration would bring a ship to roughly 77% of light speed. 2 years would reach about 97%. 3 years would push past 99%. The gains slow down as you approach light speed. Each additional year of thrust adding a smaller increment of speed, but time dilation compensates for this, compressing the traveler's subjective experience of the journey even as the raw acceleration becomes less efficient. All of this brings us naturally to one of the strangest and most carefully studied consequences of relativity, usually called the twin paradox. Picture 2 twins, Alice and Bob. Alice boards a relativistic spacecraft and travels to a star 20 light years away at 90% of light speed. Bob stays behind on Earth. From Bob's point of view, watching from home, Alice's outbound trip takes about 22 years. Her return trip takes another 22. By the time she's back, Bob has aged 44 years, growing from a young adult into someone approaching retirement, while waiting for his sister to come home. From Alice's perspective, aboard the ship, time dilation compresses each leg of the trip at 90% of light speed, with gamma at about 2.3. Her 22-year outbound journey feels to her like only about 9.5 years. Her return trip feels the same. In total, Alice experiences about 19 years of travel, while Bob experiences 44. When she steps back onto Earth, she's 19 years older than when she left. Bob is 44 years older. Twins, born on the very same day, are now separated by 25 years of biological age. Alice might have only the faintest hint of grey in her hair. Bob's might have gone completely white. This scenario troubled some early critics of relativity, because motion is, after all, relative. From Alice's point of view aboard the ship, couldn't it just as easily be said that Bob was the one who moved away and came back? So why does Alice end up younger, rather than Bob? The resolution comes down to the fact that their experiences weren't actually symmetrical. Alice experienced acceleration when her spacecraft changed velocity to turn around and come home. Bob did not. That asymmetry is what breaks the tie between their two reference frames, and determines, unambiguously, who ends up younger. This isn't just an abstract thought experiment. It's been tested directly. In 1971, physicists Joseph Haffel and Richard Keating flew extremely precise cesium atomic clocks around the world aboard ordinary commercial airliners, then compared them to identical clocks that had stayed on the ground. The clocks that had flown had gained a small amount of time compared to the stationary ones, by about 270 billionths of a second, exactly matching what special relativity predicted. The effect was tiny, because airplane speeds are tiny compared to light speed, but it was real, measurable, and it confirmed, in a very concrete way, something Einstein had worked out purely through reasoning, nearly a century earlier. Time dilation also creates some genuinely strange possibilities for relativistic travelers. Beyond the simple matter of aging differently, information broadcast from Earth could still reach a traveling spacecraft, allowing the crew to receive news and messages from home throughout the journey. But because of the time dilation, they would receive that information compressed. Years of Earth broadcasts arriving during just months of ship time, letting a crew watch decades of Earth's history unfold in a kind of accelerated playback. Children growing into adults, adults growing old, all within a much shorter span of their own lived experience. Sending messages the other way is trickier. A traveler moving at 99% of light speed, heading toward a star 100 light years away, would experience the journey as taking about 14 years. But any message sent back to Earth partway through the trip would still take decades to arrive, traveling at the speed of light through ordinary space, and Earth's reply wouldn't get back to the traveler until long after they'd already reached their destination. The conversation, in a real sense, falls permanently out of sync. The visual experience of traveling this fast would be strange too. Light coming from directly ahead of the ship gets blue shifted, its frequency pushed upward by the spacecraft's motion toward the source. The same kind of effect that changes the pitch of a passing ambulance siren, but for light instead of sound. Stars ahead would shift from their normal colors toward blue, then ultraviolet, then eventually into X-ray frequencies as speed increases. The familiar constellations becoming sources of radiation invisible to the human eye, detectable only by instruments. Light from behind the ship experiences the opposite effect. Redshifted, stretched toward longer wavelengths, drifting from visible light into infrared, and then into radio waves, eventually fading below the threshold of detection. There's also a visual distortion called relativistic aberration, which bends the apparent position of light arriving from the sides of the ship, compressing it forward into a narrowing cone in the direction of travel. At 90% of light speed, this effect squeezes most of the visible sky into a circle spanning about 60 degrees directly ahead of the ship. At 99%, that circle narrows to around 16 degrees. At higher speeds still, the entire visible universe would collapse into a single brilliant point of light straight ahead, with complete darkness everywhere else. And then there's the question of what's actually out there, in the space between stars, waiting for a fast-moving traveler. Space between the stars isn't perfectly empty. Each cubic centimeter of it contains, on average, about one hydrogen atom, along with faint traces of helium, heavier elements, and scattered dust. At low speeds, this material is essentially harmless. A spacecraft passes through it the way a bullet passes through air, barely registering its presence. At relativistic speeds, that same thin material becomes something far more dangerous. Each hydrogen atom strikes the hull with kinetic energy that scales with the square of the gamma factor. At 90% of light speed, each of those impacts delivers energy comparable to a cosmic ray particle. At 99%, the energy climbs by another factor of about 20. The forward surfaces of a fast-moving ship would face a continuous, fine sleet of high-energy particles, capable of damaging electronics, degrading materials over time, and penetrating biological tissue. Shielding against this would require either substantial physical barriers, or active systems using magnetic fields to deflect incoming particles before they ever reach the hull. Though the field strength needed grows along with speed, physical shielding, meanwhile, adds mass, and that added mass has to be accelerated too, compounding the entire energy problem. Despite these very real engineering challenges, the underlying physics of relativistic travel is settled and well confirmed. Time dilation isn't a strange theoretical curiosity. It's a measured, repeatedly verified phenomenon. The equations genuinely allow for human travel across interstellar and even intergalactic distances within a single biological lifetime. What stands between us and that possibility isn't physics. It's propulsion technology. So what kinds of engines might actually get us there? What could possibly deliver the staggering amounts of energy that relativistic travel demands? Let's walk gently through some of the ideas, from the merely audacious to the genuinely speculative. Perhaps the boldest propulsion concept ever seriously studied by mainstream engineers is something called nuclear pulse propulsion. The idea took shape in the late 1950s at the General Atomics Laboratory in San Diego, where a group of physicists asked a question that sounds almost absurd on its face. What if you could harness the energy of nuclear explosions directly for spacecraft propulsion? What if, instead of containing that energy inside a reactor, you simply detonated small nuclear devices behind your ship and rode the resulting blast waves outward? This became known as Project Orion, and it drew in some remarkable scientific minds, including physicists Freeman Dyson and Theodore Taylor, who spent years turning what sounded like a wild idea into careful, detailed engineering plans. These weren't dreamers indulging in fantasy. They were serious researchers, running rigorous calculations and actual physical experiments. The basic concept works like this. A spacecraft carries a supply of specially designed nuclear devices. These are ejected one at a time from the rear of the vessel and detonated at a carefully calculated distance behind it. Each explosion creates an expanding plasma fireball. A large, heavy pusher plate mounted on the back of the spacecraft absorbs the fraction of that plasma that strikes it, transferring momentum forward. A system of shock absorbers positioned between the pusher plate and the crew compartment smooths the violent impulses into something closer to a tolerable, rhythmic push. The Orion team actually built and tested small-scale models, using conventional chemical explosives rather than nuclear ones, and the concept worked in practice. The little models flew. The pusher plates survived repeated blasts. The shock-absorbing systems performed as designed. Nuclear test ban treaties brought the program to a halt in 1963. before any actual nuclear detonations could be tested in this configuration. But the underlying physics had already been validated through these smaller experiments. Calculations from the project suggested that Orion-style propulsion could outperform any other propulsion concept proposed before or since. A modest design using fission-based devices might reach 3 to 4% of light speed. Larger designs, incorporating hydrogen fusion devices, could potentially reach 8 to 10%. The most ambitious versions, requiring engineering capability well beyond what existed in the 1960s, might push past 15% of light speed. At 10% of light speed, a journey to Tau Ceti, a sun-like star about 12 light-years away that may host potentially habitable planets, would take roughly 120 years. That's still longer than a single human lifetime, but well within reach of a multi-generational mission, or of travelers prepared to spend most of their lives in transit. At this relatively modest speed, time dilation offers only a small benefit, compressing the journey by less than 1%. The crew would experience a duration very close to what observers back on Earth would. Measured. The engineering hurdles for nuclear pulse propulsion are significant, but probably not insurmountable. The pusher plate would need to withstand repeated exposure to nuclear fireballs, with temperatures in the millions of degrees arriving in brief pulses, potentially thousands of times across a full journey. Materials science has advanced enormously since the 1960s, and modern composites and heat-resistant metals might well be up to the task. The shock absorption system would need to turn those violent impulses into smooth, survivable acceleration, a problem that looks solvable with enough engineering effort. There are obvious safety concerns too, around carrying thousands of nuclear devices through launch and transit, and a catastrophic failure could scatter radioactive material widely or destroy the mission outright. Even so, nuclear pulse propulsion requires no new physics and no materials beyond what we already understand. Of every concept on this list, it's the nearest to something we could plausibly build using only what we know today. A later study, called Project Longshot, carried out by the United States Naval Academy in the late 1980s, examined a fusion-powered variant of this same basic idea, using small fusion detonations instead of fission ones. For greater efficiency and reduced radioactive hazard, the study concluded that a mission to Barnard's star, about 6 light-years away, could be reached in roughly 100 years, at around 4.5% of light speed, using technology the study's authors believed could realistically be developed within a few decades. A very different approach comes from antimatter propulsion, which offers an energy density that dwarfs every other known fuel source, while still remaining grounded in well-understood physics. When a particle of ordinary matter meets its antimatter counterpart, the two completely annihilate each other, converting the entirety of their combined mass directly into energy. Compare that to nuclear fission, which converts only about 0.1% of its mass into energy, or nuclear fusion, the process that powers stars, which manages somewhere around 0.7%. Antimatter is roughly 140 times more energy dense than fusion, and about 1,000 times more efficient than fission. A single gram of antimatter, annihilating with a gram of ordinary matter, releases something like 180 trillion joules of energy. That's comparable to the explosive yield of the atomic bomb dropped on Hiroshima. It's also roughly equivalent to the total energy an average American household uses across 4.5 years. In principle, it could push a small spacecraft to velocities that chemical rockets could never reach. No matter how much fuel they carried, an antimatter rocket would generate thrust by directing the products of matter. Antimatter annihilation through a magnetic nozzle. When an electron meets its antimatter counterpart, a positron, both vanish and release gamma rays. When a proton meets an antiproton, the result is a spray of particles called pions, which can be guided magnetically, and which then decay further into muons, themselves still magnetically steerable, before finally decaying into electrons and neutrinos. The exhaust velocity achievable through this process approaches a meaningful fraction of light speed itself, far beyond anything chemical, fission, or fusion-based systems can manage. This extreme exhaust velocity completely transforms the rocket equation that so severely limits chemical propulsion. With antimatter, reaching relativistic speeds becomes a question of engineering and resources, rather than something blocked by the sheer impossibility of carrying enough fuel. Consider a journey to Epsilon Eridani, a young sun-like star about 10.5 light-years from Earth, known to host at least one confirmed planet, at 30% of light speed, achievable with roughly 100 kilograms of antimatter for a modest probe. The journey would take about 35 years from Earth's point of view. Time dilation at this speed compresses the traveler's experience only slightly, to around 33 years, a modest but real reduction. A person could leave Earth at 30 years old and arrive at Epsilon Eridani at a subjective age of 63, still potentially vigorous enough to take part in exploring it. Scaling up the antimatter supply allows for higher speeds, with correspondingly larger time dilation benefits. Several thousand kilograms of antimatter could theoretically push a crewed vessel to 70 or 80% of light speed. At those speeds, the journey to Epsilon Eridani would still take 13 to 14 years from Earth's perspective, but the traveler's own experience would compress to somewhere around 8 or 9 years. A trip that once seemed to demand most of a human life becomes something closer to a long but very manageable expedition. The real obstacle with antimatter isn't the physics, it's production. Antimatter doesn't exist naturally anywhere in significant quantities, anywhere we've found in the universe. Every bit of it used for propulsion would have to be manufactured through particle accelerator collisions that demand enormous amounts of input energy. Current global antimatter production amounts to perhaps 10 to 20 nanograms per year, generated mainly at facilities like CERN in Switzerland and Fermilab in the United States. To put that in perspective, gathering the 100 kilograms of antimatter needed for that modest trip to Epsilon Eridani at current production rates would take roughly 5 billion years. The energy cost only deepens the problem. Producing antimatter through particle collisions consumes roughly 10 billion times more energy than the antimatter ultimately stores. Manufacturing enough for a single interstellar probe would require energy inputs exceeding the entire power consumption of human civilization across centuries, or even millennia. Storage presents its own serious difficulty. Antimatter annihilates instantly on contact with ordinary matter, so it has to be suspended in a perfect vacuum using magnetic fields, never touching any physical container wall, remaining stable through the vibrations of launch, and surviving decades of storage during an interstellar crossing. The longest antimatter has ever actually been stored is about 16 hours, achieved at CERN in 2023. Scaling that up to decades would require an improvement of roughly 10,000 times. These production and storage challenges push antimatter propulsion well into the distant future, if it ever becomes practical at all. The physics is beautiful. The engineering remains, for now, far beyond reach. There's a third approach that sidesteps the core problem facing every rocket-based idea so far. Every rocket has to carry its energy source along with it, and that energy source has mass, which itself has to be accelerated, creating a kind of vicious circle, where adding more fuel for speed also adds more mass that then needs even more fuel to move. Beamed energy propulsion breaks that circle. by leaving the power source behind on Earth. The idea traces back to the 1960s, when physicist Robert Forward proposed using powerful lasers to accelerate lightweight sails to interstellar speeds. A sail carrying no fuel at all could simply reflect photons, gaining momentum directly from the light itself. With a powerful enough laser and a sufficiently lightweight sail, speeds approaching a meaningful fraction of light speed become theoretically achievable. The most serious modern attempt at this is a project called Breakthrough, announced in 2016 with $100 million in initial funding from the entrepreneur Yuri Milner, and publicly supported by the physicist Stephen Hawking before his death. The plan envisions a ground-based array of lasers accelerating tiny spacecraft, nicknamed starships, up to about 20% of light speed. At that speed, the journey to the Alpha Centauri system would take roughly 20 years. The concept calls for a phased laser array with a combined power output approaching 100 GeV, roughly equivalent to the output of 100 large nuclear power plants running simultaneously. This array would focus its beam on a spacecraft weighing only a few grams, consisting of a reflective sail a few meters across, attached to a tiny chip carrying a camera, communications equipment, and navigation instruments. The intense pressure of the light would accelerate this gossamer craft from a standstill to 20% of light speed in about 10 minutes. The engineering challenges are enormous, though perhaps not impossible. The laser array would need to maintain a tight, coherent focus on a target that's accelerating away at tremendous rates, eventually receding to distances where the time delay for light to travel between the laser and its target stretches first to seconds, then to minutes. The sail itself would need to survive radiation intensities that would vaporize ordinary materials, requiring advanced reflective coatings that remain, for now, largely theoretical. And the tiny chip would need to carry working scientific instruments while weighing less than a standard paperclip. Even so, Breakthrough Starshot offers some genuine advantages over other interstellar concepts. The laser array stays on Earth, where it can be powered by ordinary terrestrial energy, maintained, upgraded, and reused for many separate missions. Each individual starship is cheap enough that hundreds or thousands could be launched at once, improving the odds that at least a few survived the journey and sent back useful data. The fundamental limitation of this approach, for human travel specifically, lies in deceleration. A laser-propelled sail speeds up by reflecting light from behind. It has no way to slow down using that same mechanism, because there's no laser waiting at the destination to push back against it. A Breakthrough Starshot probe would streak through the Alpha Centauri system at 20% of light speed, getting only a few brief minutes to gather data, before continuing on forever, never able to stop. Beyond these concepts, grounded in physics we already understand, there are a few far more speculative ideas worth mentioning, more for what they reveal about the boundaries of current physics than for any near-term plausibility. The Alcubierre warp drive, proposed by the Mexican physicist Miguel Alcubierre in 1994, describes a configuration of space-time that would allow something like faster-than-light travel, without actually violating special relativity. The idea works by contracting space ahead of a spacecraft, while expanding space behind it, creating a kind of bubble of ordinary flat space-time that rides along on a wave in the fabric of the universe itself. Inside the bubble, the spacecraft stays still, relative to its own local patch of space. No speed limit is broken, because the ship never actually moves through space in the conventional sense. Instead, space itself is doing the moving, carrying the bubble and everything inside it. Forward. The mathematics of this idea work within the framework of general relativity. The equations describe something physically consistent, if deeply exotic. But creating this configuration requires something called negative energy density, a property that may not actually exist anywhere in nature. The most optimistic calculations put the energy requirement at something like the mass energy of the planet Jupiter. More realistic estimates push the figure well beyond the mass energy of the entire observable universe. The Alcubierre drive remains a fascinating, mathematically valid idea. With no apparent path toward physical construction, wormholes offer another speculative route, one that would, in principle, bypass the velocity problem entirely. These are theoretical structures, permitted by general relativity, that would connect to distant points in space-time through a kind of shortcut outside ordinary three-dimensional space. A traveler entering one mouth of a wormhole might emerge from the other mouth light-years, or even billions of light-years away, having effectively crossed zero ordinary distance along the way, keeping a wormhole open and stable. Enough to actually travel through would require exotic matter with negative energy density, and whether such matter can exist at all remains an open question. Some calculations from quantum field theory suggest that very small amounts of negative energy density might be achievable through certain quantum effects, but whether that could ever be scaled up to stabilize something large enough for a spacecraft to pass through is entirely speculative. And even setting that aside, using a wormhole for travel still requires getting one of its two mouths to the desired destination in the first place, which brings back, in a different form, the very propulsion problem wormholes were meant to solve. Coming back to ideas grounded firmly in known physics, the most realistic frontier for interstellar propulsion in the coming century probably lies with advanced fusion systems, perhaps combined with some form of beamed energy for the initial acceleration phase. These approaches could plausibly reach speeds of 15 to 20% of light speed, assuming sustained research investment over many decades. At 20% of light speed, the time dilation benefit is real but modest, with gamma at about 1.0 to 1. 50 years of Earth time would compress to about 49 years of shipboard time, a gain of roughly 1 year over the course of the whole journey. Enough to notice, not enough to fundamentally change the experience of the trip, reaching speeds where time dilation provides truly dramatic benefits, somewhere above 50% of light speed, and ideally above 90%. Requires propulsion advances that can't currently even be drafted on paper. The gap between 20% and 90% of light speed may represent the single most difficult barrier in all of propulsion physics. No known technology bridges it with any plausible fuel source or energy supply we can currently imagine. And yet, the laws of physics themselves place no prohibition on relativistic travel. The equations permit speeds arbitrarily close to light, limited only by how much energy is available for acceleration. Time dilation genuinely compresses subjective journey times for travelers, turning distances that once seemed impossible into something merely profoundly difficult. The universe doesn't appear to have built barriers against the idea of interstellar exploration. It has simply set the price of admission extraordinarily high. Whether humanity will ever develop the technology to reach highly relativistic speeds remains genuinely uncertain. The engineering is immense. The energy requirements outstrip our current capabilities by factors that are difficult to even hold in mind. The timescales for development stretch across many human generations, demanding a kind of sustained commitment that civilizations don't always manage to maintain. But the underlying physics works. The mathematics is clear and consistent. Given enough speed, a single human lifetime really could span distances that light itself takes thousands or millions of years to cross. Let's take a step back now and ask a different kind of question. Suppose propulsion were never the problem at all. Suppose some future civilization had solved it so completely that spacecraft could routinely reach 99.999% of light speed, essentially at will. What would the ultimate limit on human travel actually become once engineering is no longer the obstacle? The answer, it turns out, doesn't come from engineering at all. It comes from the structure of the universe itself. Even with propulsion capabilities that might as well be magic, the geometry of cosmic space sets boundaries that no technology can ever cross. These boundaries are written into the expansion of the cosmos, and into the finite age of everything that exists, and they define the absolute outer reach of any traveler, no matter how fast they move, or how long they live to understand them. It helps to start with the idea of the observable universe. This is the sphere, centered on Earth, that contains every bit of light that has had time to reach us since the very beginning of cosmic history. It extends about 46.5 billion light-years in every direction, for a total diameter of roughly 93 billion light-years. Within that volume sits something like 2 trillion galaxies, each one home to hundreds of billions of stars, many of which likely host planets of their own. It would be natural to assume this sets the outer limit for any possible journey. After all, nothing beyond this boundary has ever been detected by any telescope, any radio antenna, any instrument humanity has ever built. In a very real sense, this sphere represents the entire universe accessible to human knowledge, at least for now. But here's the subtlety. The observable universe is not the same thing as the reachable universe, and the difference between the two matters enormously for anyone hoping to actually travel somewhere distant. Rather than simply look at it, the light reaching us today, from the very edge of what we can observe, began its journey over 13 billion years ago, when the universe was young and much smaller than it is now. During all that travel time, the expansion of space stretched the distance between those ancient light sources and our present location. Galaxies that emitted their light 13 billion years ago now sit, by current measurements, around 46 billion light-years away, carried outward simply by the ongoing expansion of space itself. And that expansion isn't just continuing, it's accelerating. In 1998, 2 separate research teams, studying distant exploding stars called supernova, discovered that the universe's rate of expansion has been increasing over time, rather than slowing down as everyone had expected. This acceleration is driven by something called dark energy, a mysterious component that appears to make up roughly 68% of the universe's total energy content, and its influence means that distant galaxies are, in a sense, receding from us a little faster with every passing year. This discovery earned the Nobel Prize in Physics in 2011, and it fundamentally changed our understanding of where the universe is headed. Dark energy's influence creates a boundary that matters more, for our purposes, than the observable horizon. It's called the Hubble sphere, and it marks the distance at which the expansion of space itself reaches the speed of light. Objects sitting right at this boundary, currently around 14 billion light-years from Earth, are receding from us at exactly the speed of light, 186,000 miles per second. Beyond the Hubble sphere, galaxies recede from us faster than light. This doesn't violate special relativity, because those galaxies aren't actually moving through space at faster than light speeds. Rather, space itself is expanding, carrying them along the way a raft is carried by a swelling current, without the raft itself doing any swimming. It's a subtle distinction, but it offers no real comfort to a traveler, whether a galaxy is being carried by expanding space, or moving through it under its own power. The practical result, for us, is the same. Anything beyond the Hubble sphere is currently receding faster than any signal, or any spacecraft, could ever catch up to it. Light emitted today From a galaxy just beyond that boundary begins a journey with no possible destination. Each photon pushes forward, while the space between its source and Earth keeps expanding faster than the photon can cross it. These photons travel forever, through an ever-growing void, never reaching any observer, never delivering whatever faint message they carried about the part of the cosmos they came from. Even so, the Hubble sphere isn't quite the final word for travelers, because there's an important difference between a beam of light and a spacecraft. A photon moves at light speed the instant it's emitted and never changes its velocity again. A spacecraft, on the other hand, can keep accelerating, potentially outrunning the local rate of expansion at its current position, pushing onward into regions that light leaving Earth today could never reach at all. The true boundary for a traveler is called the cosmological event horizon. Right now, it sits somewhere between 16 and 17 billion light-years from Earth, and it marks the absolute maximum distance that any signal, or any traveler, departing today, could ever reach, even given infinite time and unlimited speed. Beyond this horizon, cosmic expansion has, in effect, already won the race. Space is stretching faster than any approach velocity could ever make up for. Destinations out there aren't simply difficult to reach, they're impossible to reach, by any means consistent with the physics we understand. And this event horizon isn't fixed in place either. As dark energy continues driving the acceleration of cosmic expansion, the horizon actually shrinks over time. Regions that are still technically reachable today will at some point in the future become permanently inaccessible, as accelerating expansion carries them beyond the line. The window for cosmic exploration is, in a very real sense, slowly closing. Current cosmological models suggest that within roughly 100 billion years, the event horizon will have contracted down to encompass only our own local group of galaxies. The Andromeda Galaxy, which is currently approaching us under gravitational attraction, will merge with the Milky Way long before that point, but every other galaxy currently visible to us will, by then, have crossed beyond the horizon, permanently out of reach. On timescales measured in trillions of years, this isolation becomes essentially complete. Future astronomers, living in whatever merged galaxy eventually forms from the Milky Way and Andromeda together, would look out and see only their own immediate galactic home. No external galaxies, no trace of the cosmic microwave background, that faint ancient glow left over from the Big Bang, because by then it would have redshifted far beyond any possible detection. Every observable trace of the universe's early history would have quietly slipped away, carried off by the very expansion that once revealed it to us. Those future astronomers might develop an entire physics and cosmology of their own, built from first principles, and quite reasonably conclude that their one galaxy was the whole of existence, never knowing that 2 trillion others once filled the sky. This creates something like a quiet, slow countdown for exploration. Every distant galaxy, every star cluster, every grand cosmic structure we might ever dream of visiting carries something like an expiration date, after which it becomes permanently unreachable. The universe offers a window for this kind of exploration, and that window, gradually, is closing. So, within these real cosmic constraints, how far could a human lifetime actually carry someone? The answer means combining the time dilation we talked about earlier with the geometry of an expanding universe, working out not just how far a traveler could go, but how far their destination will have drifted during the journey itself, at 99% of light speed. A traveler maintaining that pace for 50 years of their own subjective time would cross about 350 light years. Back on Earth, about 355 years would have passed. That distance encompasses something like 50,000 star systems, including many stars similar to our own Sun, and quite a few confirmed to host planets. Within 350 light-years lie active stellar nurseries, where new stars are still being born. Ancient star clusters older than our galaxy's own disk, and a wide variety of stellar types, from small red dwarfs that will keep burning for trillions of years, to massive blue giants destined to explode as supernova within just a few million years. A 50-year journey at this speed would open up cosmic environments very different from anything in our own neighborhood. A traveler willing to spend a full century of subjective time in transit could, in principle, reach several nearby dwarf galaxies, encountering stellar populations quite distinct from those found in our own galactic disk, Andromeda. That nearest large neighboring galaxy, sitting about 2.5 million light-years out, represents the real test case for relativistic travel within our local patch of the cosmos. Reaching it would demand either impossibly long journeys at modest speeds, or extremely relativistic ones, where the gamma factor climbs into the tens of thousands. At a gamma of about 50,000, 50 years of subjective travel time would span exactly that 2.5 million light-year distance. A traveler leaving Earth today at that speed would arrive at Andromeda having aged 50 years, while Earth itself aged 2.5 million years in the meantime. What might such a traveler find there? Andromeda holds stellar populations, both younger and older than anything in the Milky Way. Its central bulge is larger and more prominent than our own. It harbors its own supermassive black hole, estimated at about 100 million times the mass of our Sun, roughly 25 times heavier than Sagittarius A star, the one at the center of our own galaxy. It hosts dozens of smaller satellite galaxies, many with their own distinct stellar populations and planetary systems, quite unlike anything found near us. But the traveler could never share any of this with Earth. Even if they somehow sent a signal back across that 2.5 million light-year gap, the message would take 2.5 million years to arrive, by which point the civilization that sent the traveler would be lost to unimaginable antiquity. In every meaningful sense, such a traveler would become a citizen of Andromeda, rather than the Milky Way. Their journey would be a one-way departure into an entirely alien part of the cosmos, push the required gamma factor higher still, and the destinations available become genuinely cosmological in scale. The Virgo cluster, home to more than 1,300 galaxies, sitting about 54 million light-years away, becomes theoretically reachable at a gamma of around 180,000. The traveler would age 50 years, while Earth aged 54 million. Dinosaurs would have gone extinct more recently than the traveler's own departure would seem to anyone watching from Earth. The Coma cluster, roughly 320 million light-years out. The Perseus cluster, about 240 million light-years away. The great galaxy clusters that define the large-scale structure of the cosmos. The vast cosmic web that telescopes have only recently begun to map in detail. All of these fall, in principle, within reach of a single human lifetime, at gamma factors in the millions. A traveler could visit these distant cosmic cities, watch thousands of galaxies bound together by mutual gravity, and witness, directly, the architecture of the universe on scales that Earth-based telescopes can only photograph from billions of light-years away, at the most extreme end, with gamma approaching the billions. The mathematics allows for journeys spanning most of the observable universe within a single subjective lifetime. A traveler accelerating steadily at one Earth gravity, flipping at the midpoint to decelerate the same way, could theoretically reach the current edge of the observable horizon in about 45 years of their own time. They would age 45 years, while the universe around them aged roughly 28 billion years. They would arrive at places that currently exist, to us, only as ancient light still making its way to our telescopes, and they would find those places utterly transformed, evolved across cosmic timescales, far beyond recognition. But even these extreme calculations eventually run into the absolute limit imposed by cosmic expansion. The event horizon cannot be crossed, no matter how fast you go. Destinations currently beyond roughly 17 billion light-years will remain forever out of reach. Accelerating toward them simply delays the moment when expansion finally carries them permanently out of range. And there's a further complication, too. Destinations that are technically reachable today might still cross beyond the event horizon during the course of a very long journey. A traveler setting out toward a galaxy near the current edge of the horizon might discover that cosmic expansion, during their own voyage, has carried their intended destination permanently beyond reach. The accessible universe is quietly shrinking, even as travelers attempt to explore it. This one-way nature of extreme relativistic travel carries some genuinely profound implications. Time dilation lets you reach enormous cosmic distances while aging only modestly, but it doesn't let you return to the era you departed from. Every journey like this becomes, in effect, a journey forward through time, from which there's no way back. Consider something more modest. A round trip to the Pleiades cluster, about 440 light-years away, at 99% of light speed. The outward leg alone would take about 445 years of Earth time, but only around 63 years of ship time. The return trip adds roughly the same again. The traveler would come home having aged about 126 years, only to find that nearly 900 years had passed on Earth in their absence. The civilization that sent them would be ancient history. Languages would have drifted beyond recognition. Political systems, cultural values, entire ways of life, all transformed across the better part of a millennium. The traveler would return as something like a living artifact from a vanished age, perhaps studied, perhaps revered, but certainly cut off from every human connection they had once known. Longer round trips deepen this isolation further. A round trip to our galaxy's center, at 99.99% of light speed, would return a traveler to an Earth roughly 520,000 years in its own future. Modern humans have existed for only about 300,000 years, so the Earth awaiting the traveler's return would be separated from their original departure by more time than our entire species has existed. A round trip to Andromeda, if it was somehow achieved at sufficiently extreme speeds, would return a traveler to an Earth 5 million years in its future. 5 million years ago, the human lineage hadn't yet branched off from our other great ape relatives. Whatever beings inhabited Earth by the time such a traveler returned would likely be as different from us as we are from those distant ancestors. These numbers point to something that sets relativistic travel apart from every other kind of journey in human history. The voyages that shaped our past, Columbus crossing the Atlantic, Magellan circling the globe, Lewis and Clark mapping the American West, even the Apollo astronauts traveling to the moon and back, all of them preserved a connection between the traveler and home. Letters could still be exchanged. Travelers could return to families who remembered them. The fabric of human relationships survived the distance. Relativistic journeys sever that connection completely. A traveler departing Earth for distant stars, at speeds where time dilation becomes truly significant, accepts a kind of permanent exile, not just from their home planet, but from their entire historical era. They become, in a real sense, travelers through time as much as through space, moving only forward with no way to revisit the past they left behind. Even returning to the exact same physical coordinates on Earth, they would arrive in a foreign future, one that shares only its location with the world they once knew. This reframes the whole question we started with. How far could a human travel in one lifetime becomes, in the end, a question about trade-offs between range and connection, between exploration and belonging, between discovery and the simple comfort of return. Different people, faced with this choice, would likely answer differently, depending on what they value most. For someone willing to give up their past entirely in exchange for the journey, the theoretical maximum reach extends across nearly the whole of the observable universe. A lifetime measured in subjective decades could, in principle, span distances of billions of light years, reaching some of the most remote galaxies our best instruments can currently detect. The universe, it turns out, permits exploration on a scale that would have seemed like pure fantasy to even the most imaginative science fiction writers, for travelers hoping to return within a few centuries of Earth time, while keeping some realistic chance that a recognizable human civilization still exists when they arrive home. The practical range falls dramatically to perhaps a few hundred light years. That still encompasses hundreds of thousands of star systems, and quite possibly billions of planets, but it represents only a tiny corner of our own galaxy, an almost vanishingly small fraction of the cosmos as a whole. There's something worth sitting with in all of this, about what these calculations reveal about humanity's place in the universe. We exist inside a cosmos that permits exploration on a scale that vastly exceeds anything our imaginations are naturally built to handle. The laws of physics don't trap us within our own solar system. They offer, at least in principle, genuine pathways outward, toward other stars, other galaxies, toward cosmic structures spanning hundreds of millions of light years. The barriers we currently face are technological, not physical. They reflect our present inability to generate the kind of energy that relativistic propulsion requires, not some fundamental limit written into nature itself. The universe doesn't seem to have built prisons for biological life. It has, instead, left open a set of genuine, if extraordinarily demanding, pathways that could one day carry conscious beings to the farthest reaches of observable reality. A single human lifetime, measured in the traveler's own subjective years, could theoretically encompass journeys vast enough to humble even the grandest myths of earlier ages, starting from one small rock, orbiting one ordinary star. Inside one unremarkable galaxy among trillions, a person could, in principle, live long enough to witness galactic superclusters containing thousands of galaxies bound together by gravity, vast cosmic voids spanning hundreds of millions of light years, and the great elementary structure that organizes matter across the largest scales we can measure. And yet these same calculations also reveal something quietly humbling about our place in all of it. Even with flawless, limitless technology, most of the universe remains forever beyond reach. The cosmic horizon recedes as you approach it, carried steadily outward by the same expansion that defines the era we happen to live in. The great majority of galaxies we can currently observe have, in a sense, already crossed beyond any real possibility of contact. We see their ancient light, faithfully arriving after its long journey, but we can never actually visit the places that light came from. Of the roughly 2 trillion galaxies that populate the observable universe, perhaps only about 1 in a million, those within our own local supercluster, might ever realistically be reached, before cosmic expansion eventually carries them beyond our event horizon for good. All the rest exist, for us only as images, light that has traveled for billions of years, painting pictures on our telescopes of places we will, almost certainly, never go. None of this diminishes what it would mean to actually reach the stars. It simply places that achievement inside a larger, honest picture of how the universe itself is built. Humanity could conceivably become a genuinely interstellar civilization, spreading across hundreds, or even thousands of light years, settling worlds throughout our own arm of the galaxy, and still occupy only an infinitesimally small fraction of all the space that's theoretically accessible. We could, in time, become a civilization spanning the entire Milky Way, and still represent, in the grand cosmic picture, something like a single grain of sand on an unimaginably vast beach. So the question we started with, how far a person could actually travel in one lifetime, ends up becoming a question less about physics and more about what kind of journey we'd actually be willing to take. The physics, it turns out, permits almost anything we might dream of. The engineering remains an enormous, open challenge. But underneath even that, the choice of where to go and how far touches on something deeper, questions about identity, connection, and what exploration itself is ultimately for. A traveler departing for Andromeda accepts, in effect, a one-way ticket into an entirely separate cosmos. They would never again see the face of anyone alive in their original era. They would never get to share what they discovered with the civilization that made the journey possible in the first place. They would become, in a very real sense, the starting point of an entirely new branch of humanity, planted in unfamiliar soil, disconnected from the tree that produced them. Perhaps a traveler like that would find real meaning in being a kind of cosmic pioneer. Perhaps simply knowing that human consciousness had spread beyond its home galaxy would feel like enough to justify whatever was given up to make it happen. Perhaps the sheer wonder of standing somewhere among Andromeda's trillion stars would be its own kind of compensation for everything left behind on Earth, or perhaps, for most people, connection matters more than exploration ever could. Perhaps the destinations worth choosing are the ones that still allow for a return, that preserve some thread linking the traveler back to home, that keep alive the simple possibility of sharing what was found with the people who stayed behind. There's no single, universal answer to this. Different people, faced with the same physics, would likely make very different choices. Some would push outward, toward the very edge of what's reachable at all, chasing the farthest possible limits of human experience. Others would stay closer to home, weighing wonder against connection, range against the comfort of return. The universe itself doesn't seem to favor either choice. It offers the same equations, the same time dilation, the same rate of cosmic expansion to every traveler, in every direction. What anyone actually does with those possibilities remains entirely a human decision. It's worth pausing here, gently, on what we still don't know, because there's quite a lot of it, and it's part of what keeps this whole subject genuinely alive. Rather than settled, we don't yet know what dark energy actually is. We can measure its effects with real precision. The steady acceleration of cosmic expansion, the way it shapes the ultimate fate of every galaxy we can see. But its underlying nature remains one of the largest open questions in all of physics. Some researchers think it may turn out to be a true cosmological constant, a fixed, unchanging property woven permanently into the structure of space-time. Others suspect it might be a dynamic field, one whose strength could, in principle, shift over the vast span of cosmic time. Upcoming observatories, including survey telescopes designed specifically to map the distribution of galaxies across billions of light-years with much greater precision than before, are actively working to narrow down which of these possibilities, or perhaps some other one entirely, best matches what we actually observe. We also don't fully understand whether the exotic forms of matter that warp drives and stable wormholes would require, material with what's called negative energy density, can exist in any meaningful, usable quantity, anywhere in nature. Certain quantum effects do seem to permit tiny, fleeting amounts of something like it under very specific laboratory conditions, But whether that could ever scale up to something large enough to matter for actual travel remains genuinely unresolved. More a question for theoretical physics than engineering, at least for now. On the more immediate, practical side, today's spacecraft propulsion research is advancing steadily, even if not yet anywhere near relativistic speeds. Engineers continue refining ion propulsion systems, pushing toward greater efficiency and longer operational lifetimes for missions across our own solar system. Various research groups continue studying nuclear thermal and nuclear electric propulsion, technology that, as we touched on earlier, has already been tested successfully, and that some space agencies are revisiting for future crewed missions, particularly to Mars, where shorter, more energy-efficient transit times would meaningfully reduce a crew's exposure to space radiation during the journey. Breakthroughs. The laser-propelled sail concept remains an active area of theoretical and early engineering study, even though a working full-scale system likely remains decades away. At the very least, researchers continue investigating the materials science questions at its core, particularly how to build reflective sails capable of surviving the intense radiation pressure of a powerful laser beam without simply melting or tearing apart. Antimatter research continues to mostly aimed at entirely different goals than propulsion. Fundamental physics experiments exploring the deep symmetry or possible asymmetry between matter and antimatter, work that helped earn a Nobel Prize in Physics as recently as the 2020 year range for related antimatter research. Any eventual application to spacecraft propulsion remains, for now, a distant secondary possibility, resting on production and storage capabilities that don't yet exist at anywhere near the necessary scale. And there's a broader, more reflective question that continues to occupy physicists and astronomers alike. Beyond any particular piece of engineering, does intelligent life elsewhere in the universe face exactly these same constraints, the same brutal energy requirements, the same vast gulfs between stars? Or might there be physical principles we simply haven't discovered yet, ones that could open up possibilities entirely outside what current physics allows? Most researchers remain genuinely cautious here, reluctant to assume that some entirely new shortcut is waiting to be found, since every test of relativity so far, across more than a century of careful experiments, has only ever confirmed Einstein's original framework more precisely, never revealed any hidden exception. But the questions themselves remain open, honestly open, and that's part of what makes this such a genuinely active, living area of science, rather than something closed and finished. What makes the whole subject so quietly compelling, in the end, isn't really the prospect of any specific mission, since nothing remotely like interstellar travel is likely within the coming century, at the very least. It's the way this single question, how far could a person travel in one lifetime, manages to connect almost the entirety of modern physics into one continuous, coherent thread. Basic Newtonian mechanics, where rockets first started, relativity, both special and general, with time dilation as easily its most genuinely surprising and well-confirmed prediction, particle physics through the antimatter question, cosmology through dark energy and the expansion of space itself, nuclear physics through fission and fusion-based propulsion ideas. All of it converges, eventually, on a single, almost childlike question about how far one person could really go. In one normal human life, the stars, in the end, aren't impossibly distant in any absolute sense. They're simply waiting for us to develop the means to reach them. The distant galaxies aren't forever sealed away, either. Reaching them would require nothing more exotic, in principle, than sufficient velocity, and a willingness to accept the very real temporal consequences such a journey would bring. Hidden inside the equations that govern motion through space and time lies a genuine, mathematically sound promise. That distances measured in millions of light years could, conceivably, someday fall within reach of a single human life. That promise is written directly into the mathematics of relativity, verified now by more than a century of careful, repeated experiments. And it simply waits for the engineering that would turn theoretical possibility into something practically real. The universe, in its own quiet way, leaves the door open. Somewhere between the 430,000 miles per hour we've already achieved, and the speeds where gamma climbs into the millions, there sits a long, difficult threshold, where human cosmic exploration shifts gradually from fantasy into something approaching genuine, distant possibility. So, how far could a human actually travel in one lifetime? The honest answer is, it isn't ultimately limited by physics at all. It's limited by imagination, by patience, by sustained determination across generations, and by our own willingness to pay whatever price the universe quietly asks, in exchange for passage to the stars. For now, we remain here on this one small blue planet, circling an ordinary star in an ordinary corner of an ordinary galaxy, looking outward at a universe vastly larger than anything we can fully picture, knowing the physics would, in principle, allow us to go almost anywhere within it, and knowing, too, just how much would have to be built and given up to actually make that journey real. It's a strange kind of comfort in its own way. The barriers aren't really walls at all. They're simply distances, waiting patiently, the way distances always have, for whoever eventually decides to cross them. And on that quiet thought, we'll leave it here for tonight.